Hello, and welcome. In this video, we will explain what you need to know in order to apply recurrent neural networks to language modeling. Language modeling is a gateway into many exciting deep learning applications like speech recognition, machine translation, and image captioning. At its simplest, language modeling is the process of assigning probabilities to sequences of words. So, for example, a language model could analyze a sequence of words and predict which word is most likely to follow. So with the sequence "this is an," which you see here, a language model might predict that the word "example" is most likely to follow, with an 80% probability. This boils down to a sequential data analysis problem. The sequence of words forms the context, and the most recent word is the input data. Using these two pieces of information, you need to output both a predicted word and a new context that contains the input word. Recurrent neural networks are a great fit for this type of problem. At each time step, a recurrent net can receive a word as input and the current sequence of words as the context. After processing, the net can then form a new context and repeat the steps until the sentence is complete. The main metric for language modeling is known as perplexity. Perplexity is a measure of how well the model is able to predict a sample. Keep in mind that a low perplexity rating equates to a larger amount of confidence in the prediction, so we want our model to have as low of a perplexity rating as possible. When it comes to actually training and testing a language model, you'll find that good datasets are hard to come by. Since the data points are words or sentences, the data has to be annotated, or at least validated, by a human. This is time-consuming and typically constrains the dataset's size. One of the biggest datasets for language modeling is the Penn Tree Bank. The Penn Tree Bank was created by scholars at the University of Pennsylvania. It holds over 4 million annotated words in many different types of classifications. In order to build such a large dataset, all of the words were first tagged by machines and then validated and corrected by humans. The data comes from many different sources, from papers published in the Department of Energy to excerpts from the Library of America. As we mentioned, the Penn Tree Bank is the go-to dataset for language modeling and natural language processing in general. The Penn Tree Bank is versatile, but if you're only interested in predicting words rather than meaning or part of speech, then you don't need to use the tags in the dataset. An interesting way to process words is through a structure known as a word embedding. A word embedding is an n-dimensional vector of real numbers. The vector is typically large, with n greater than 100. The vector is also initialized randomly. You can see what that might look like with the example here. During the recurrent network's training, the vector values are updated based on the context that the word is being inserted into. So words that are used in similar contexts end up with similar positions in the vector space. This can be visualized by utilizing a dimensionality reduction algorithm, such as T-SNE. Take a look at this example here. Words are grouped together either because they're synonyms or they're used in similar places within a sentence. The words zero and none are close semantically, so it's natural for them to be close together. And while Italy and Germany aren't synonyms, they can be interchanged in several sentences without distorting the grammar. By now, you should understand the theory behind language modeling, the importance of the Penn Tree Bank, and the application of recurrent nets to language problems. Thank you for watching this video.